Hello, my name is Clint Sestrich. I'm a fisheries biologist with the Custer-Gallatin National Forest in Livingston, Montana. Today we're going to learn about the effects of wildfires on aquatic ecosystems. An ecosystem is a biological community of interacting organisms and their physical environment. In this case, the physical environment is an aquatic environment, either lakes, rivers, or streams. It's through activities like fishing that most of us are introduced to the amazing and fascinating world that lies beneath the surface of our lakes, rivers, and streams. It's through fishing that many of us can relate to these aquatic ecosystems. So, in developing an understanding of the effects of wildfire, I think a great question to ask is whether you would fish a burned stream. In order to answer this question, we must first have an understanding of fire effects. Fire effects can be direct or indirect, and they can be physical or biological. Direct effects are those that happen directly from the fire itself, and they depend on fire intensity, or how hot the fire burned, and the duration, or how long it burned. Some physical effects include combustion of the organic or living matter in the soil that can change the physical properties of the soil. Also, the water temperature of a lake, river, or stream can increase, or the chemical composition of water can even be changed temporarily as you have leaching of ammonium and phosphorus from ash that comes in contact with the water. Some biological effects that are direct from the fire itself include mortality or killing of trees. Also, if stream temperatures increase enough, it can actually kill fish and other aquatic organisms. And you also have mortality of living organisms in the soil through combustion of the soil. If a fire burns hot enough next to a stream, it can increase the temperature such that fish can't survive. Also, ash that leaches ammonium and phosphorus into the water can become toxic to fish and can result in fish kills, like this picture of some dead brown trout in New Mexico. We all know that wildfires also can negatively impact terrestrial wildlife, like these elk that sought refuge in the East Fork of the Bitterroot River from the fires of 2000. Indirect fire effects are those that happen after the fire is out, and they can occur within the perimeter of the fire or even beyond the perimeter of the fire. So they can be removed in space and time from the fire itself. The magnitude of these indirect effects really depend on burn severity, or how hot the fire burned and for how long, and that really translates to how much of the change there was in the soil physical properties. It also depends on how big of an area burned, how steep the terrain is, and the magnitude of precipitation or rain events after the fire. In order to predict what the indirect effects of fire will be, soil scientists classify the burned area into low, moderate, or high burn severity. Low burn severity typically has less than 50% of the litter layer consumed by the fire. There's some char, and needles and leaves are mostly intact. Soil with moderate burn severity has up to 80% consumption of the soil litter and duff. There can be recognizable leaves and needles in the canopy. However, that's not always a good indication of what the actual soil burn severity is. Soil classified as high burn severity has had almost all of the organic matter within the soil profile consumed by the fire. That means that the fire had to burn hot enough and for long enough to consume that organic matter in the soil. You can have a fire that burns with high intensity that consumes almost all of the leaves or needles in the trees, but it moves through so fast by a strong wind-driven event that the soil doesn't have enough time to cook and change its physical properties. So when we see high burn severity, it means that there is a hot enough fire for long enough duration to cook the soil and change the properties. One of the primary ways that the physical properties of soil are changed is that soil can become hydrophobic, meaning that it repels water once those organic components are no longer left. Soil that repels water does not have water that actually soaks into the soil profile, and instead it runs off the surface. You can expect indirect effects if a large enough area of the burn is classified as moderate to high severity. This means that there's decreased water infiltration due to hydrophobicity, and more water is running off over the surface of the land. This increases erosion and can actually increase peak flows or how high stream flows are. This can actually increase sediment delivery to stream channels, and more sediment coming into the stream channels can have some biological effects, which include decreased survival of fish, eggs, and fry, and also a decrease in macroinvertebrate abundance and diversity. Fish species like trout that lay their eggs in gravel depend on water flowing through the gravel to deliver oxygen to their eggs. If the spaces in the gravel are filled up with fine sediment, the eggs will suffocate. Here we have a picture of some eggs and fry that are living in the spaces of the gravel during this critical life stage. The indirect effects in the aftermath of a wildfire don't just depend on the burn severity, but they also depend on the intensity of precipitation events over the burned area. If you have a large precipitation event over an area with sufficient amount of hydrophobic soil, you can have extreme debris flow events and mudslides. These debris flows often originate in small draws and then precipitate downstream into larger stream channels. They can actually fill stream channels totally with rocks, mud, debris, and logs. Here we have some photos from the Bitterroot River Basin following the wildfires of 2000. Here we have an aerial photo over Laird Creek, which is a small tributary stream to the East Fork of the Bitterroot River. Unfortunately, homes in this drainage burned down from the fire itself, but then just within a year later, there were debris flows that surrounded and devastated some homes and property. Infrastructure, like bridges, roads, and utility lines, can be threatened by debris flows in the post-fire landscape. The effects of debris flows on aquatic organisms and their habitats can also be dramatic and appear devastating. They can alter the amount of large wood in a stream channel, which is an important habitat component. They can also scour channels to bedrock, and they can also fill stream channels with cobble and mud. This reduces the number and size of pools, which are an important habitat component for fish. Overall, this reduces the habitat complexity, or how good the habitat is for aquatic organisms. Ultimately, the survival and abundance of fish can be reduced, and you can actually have fish kills from these debris flows. Other indirect effects include combustion or burning up of the forest canopy and riparian or streamside vegetation. This reduces stream shading and allows more sun to enter the stream. This can actually increase the temperature of streams in the post-fire era. Here's a photo of Anderson Creek in the Mill Creek drainage south of Livingston, Montana. This stream experienced severe fire effects related to debris flows and stream heating in the post-fire era. This all looks pretty bad, right? The answer is wrong. As it turns out, wildfire isn't all bad for streams. Let's talk about why. As it turns out, wildfires and debris flows reset aquatic ecosystems and deliver the basic building blocks of healthy, complex aquatic habitats. This means that trees that are burned from the fire fall into stream channels, creating large woody debris, which actually create great hiding cover for fish and also create hydraulic conditions that sort sediment into good spawning gravel. The substrate that was delivered to stream channels from erosion and debris flow events is cleaned after a few runoff events, leaving cobble and gravel that's great for fish to spawn in and great for macroinvertebrates to colonize. Overall, this translates to great complex habitat in the post-fire era. Here we have some data from my graduate research, which examined recovery of native and non-native fish populations from the Bitterroot River Basin fires of 2000. On the left, we have the number of pools per mile, and pools are really important for fish because they provide resting places as well as places where fish can feed without spending a lot of energy. We have three different streams, Laird, Gilbert, and Rimal, on the x-axis, and you can see that over time, the number of pools per mile after the fire exceeds the number of pools per mile before the fire, except for one stream, and that's Laird Creek, but overall, the trend was that there were more pools per mile after the fire. On the right, we have the number of large woody debris pieces per mile, or pieces of wood that are greater than 1 meter in length. And we see a similar relationship. In 2009, 9 years after the fire, for every stream, we see that the number of pieces per mile far exceeds the number at the time of the fire. And this is important because fish need this large wood for cover, and they also really need the variety of velocities provided by wood in the channel. So we already said that following a wildfire, there is oftentimes less stream shading, which can increase stream temperatures. However, if temperatures don't increase too much, this can actually increase the productivity of a stream. You have more sunlight reaching the water surface, which can cause more algae growth, which is important for macroinvertebrates to feed on. This means that ultimately you have more macroinvertebrates, which are a primary food source for fish like trout. This translates to an increase in the overall productivity of these streams. Combined with large woody debris increases, more spawning gravel, a more clean cobble for macroinvertebrates to colonize, and overall increase in habitat complexity, wildfire can be a pretty good thing. One key factor affecting the rate of recovery from a wildfire is how quickly vegetation becomes reestablished on the landscape. This can happen very quickly if you don't have soil that is burned too severely. However, it can take longer if you have a large amount of high burn severity across the landscape. The photo on the left shows a stream on the Bitterroot National Forest right after the fire and then 10 years post-fire. You can see that 10 years later, we have a pretty thriving riparian community. So what about fish populations? How long does it take for them to recover from a wildfire? Here we have some fish population data collected by the Montana Department of Fish, Wildlife, and Parks, the Bitterroot National Forest, and my graduate research crew on 2 burned streams in the Bitterroot River Basin. On the left, we have Laird Creek, which was affected by the wildfire in 2000 and subsequent debris flows in 2001. And we can see that the number of fish post-fire and post-debris flow far exceeded the number of fish in the pre-fire era, especially for West Slope cutthroat, which were the most abundant species. These are native fish that actually evolved and is well adapted to fire. We see the same relationship with Chicken Creek on the right. There was actually a major fish kill on Chicken Creek from a debris flow, but in the post-fire era, we see that the number of West Slope cutthroat exceeds the number in the pre-fire era. Here we have some more fish abundance data from Meadow and Rye Creeks, which experienced high burn severity from the Bitterroot fires of 2000. On the left, we see that there's an increasing trend in the number of native West Slope cutthroat and bull trout over time, with the number of fish after the fire far exceeding the number of fish before the fire for both species. On the right, looking at Rye Creek, we see that by 2009, the number of West Slope is orders of magnitude higher than it was before the fire. Here we have some electrofishing data on Anderson Creek in the Mill Creek drainage south of Livingston, Montana. Here we see the number of native Yellowstone cutthroat before the fire in light blue and after the fire in dark blue. And we see that for the one site above a bridge where we had a monitoring reach, there was a 175% increase in native Yellowstone cutthroat trout. In the downstream reach, we see a 70% increase after the fire. Here we presented some pretty dramatic examples of aquatic habitat and fish population recovery following wildfires. However, recovery doesn't always happen this fast. It really depends on the proportion of a drainage that burned with moderate and high severity. It also depends on how stable a stream channel is in the post-fire era. Do you have debris flows that keep recurring every 1 to 5 years? Or do you have a majority of the drainage that's revegetated and stabilized to where you don't have much erosion? Recovery also depends on the extent of the initial fish population declines. Did you just have a small decline in the number of fish, or did you have complete fish kills in streams? Recovery also depends on whether you have connectivity to source fish populations. By that I mean, do you have a tributary stream that didn't burn, where fish survived that can actually repopulate an adjacent stream? And then finally, were there refugia within a stream or places that didn't burn where fish could survive and repopulate adjacent reaches of the stream? So now we circle back to our initial question. Would you fish a burned stream? This angler on Mill Creek south of Livingston, Montana would say yes, and so would I.